Hello everybody, welcome back to physics, and in this video we are going to be talking about potential energy. Now so far we've been discussing energy in terms of kinetic energy, that is the energy of motion. We've been talking about work, and that's the idea that when you do act on an object, when you interact with it, you impart energy into that object, and that energy is considered work. And potential energy is another type of energy, but this one's a little bit more interesting because it's a sort of energy storage. So we take some energy and we put it into potential energy, and basically what we're doing is we're storing it for later. Now, jumping into this topic, we are going to discuss specifically, when we talk about energy, can we relate this potential energy, and we do specifically use the word difference in potential energy. Can we relate that difference in potential energy to the work done on an object? And work, again, it should be a familiar term to us now. Work done, we've seen that before. Now we're relating it to this new term of potential energy. The other thing I want to address, and this is pretty important, what does it mean for an object to have zero potential energy? And the answer is that it's kind of an arbitrary choice, and we'll see just that. To illustrate this idea of potential energy, we are going to start off with the example of a soccer ball. And I'm going to attempt to draw a soccer ball right here. Not a perfect soccer ball, but we have a soccer ball, and what it's going to do is it's going to fall towards the ground. And as it falls towards the ground, of course, we know that it's going to speed up. And as it speeds up, it hits the ground, and after it hits the ground, the soccer ball is going to bounce, and it is going to bounce, returning upwards. So this is the scenario, right? And we've talked about falling objects in terms of Newton's laws, F equals ma. We figure out the force is the weight of the object, mg. And then once we have the force, we can say, find the acceleration. And then when you have the acceleration, you use your kinematic equation, such as v final squared is equal to v initial squared plus 2a delta y, where delta y is the height that we drop from one height to the next, right? This is one way we've looked at it, but that's a lot of steps, pretty complicated, so we say, what's another way do we do? So another way we can analyze this is through work and energy, right? We say that the work done on an object is equal to its change in kinetic energy. So if we figure out the work done on the object, we can figure out something about its motion from its kinetic energy. And what is the work done on the object? Well, the work done on the object is going to be the force, and in this case, the force is gravity, so the weight, mg. Multiply that by the height that it's dropped. And then we multiply that by cosine of the angle between the force and the displacement, right? And when we do this, we consider the two directions the ball can be traveling. Perhaps we look after the bounce while the ball is moving upwards. While the ball is moving upwards, the displacement is up, but the force is down, in which case the work done is equal to negative mgh, because theta in that case is equal to 180 degrees, when we look at the angle between the force and the displacement. Well, what about down? If our soccer ball is on its downward part of its trajectory, its displacement is a distance h downwards, its force is a downwards weight, so that means the work done is going to be equal to positive mgh. Positive because the force and the displacement have the same direction. So this is one way of working out this type of problem. And now that you know the work, you can figure out the velocity from the kinetic energy. However, this isn't the only way to do it, because something interesting happened. We see that the work on the way up is the negative of the work on the way down. These are the same values, just one is positive, one is negative. And that means that if we were to follow the ball throughout its path of moving upwards and back down, we would see that the total work done would be the summation of the work up and the work down, and those would sum to be zero. The work done on this object is zero. So what does that tell us? That tells us that the work that gravity does going one way is energy put into the object, and the work going the other way, well, it's the same amount of energy, but this time it's being removed from the object. And we can illustrate that. We can illustrate that by first looking at kinetic energy. If we look down at the bottom part of the motion down here, at the bottom we have a large velocity. I'll say that's v large, which means that we have some large amount of kinetic energy. And what happens is on the way up, the work, since it's negative, it takes energy away from this kinetic energy. So what was a large amount of kinetic energy becomes a small amount of kinetic energy at its highest point. So we would say that's Ke small. And then on the way downwards, we have plus mgh, meaning that the force of gravity is putting energy back into the ball, getting it to speed up. But we can take another path. What we can say is that between the large kinetic energy to begin with at the bottom and the small kinetic energy at the top, perhaps we define a new place, a storage. Think of this as being like a savings account for your energy, where we initially have a small amount of energy saved up, perhaps even zero. But as we go upwards, that small amount of energy starts to collect energy from that kinetic energy. It starts to take it in. And when it reaches the top, we have some large amount of kinetic energy. So our energy is storing up, meaning that what was in our kinetic energy gets transferred into the potential energy. And when it's at the top, that potential energy, it's like having a lot of savings. We can spend that savings into getting a kinetic energy back when we fall, into getting our object to speed up. So that's really what potential energy is. It's a savings account for energy. And we can save energy in a couple of different ways with very special forces. So some forces that cause this savings account of energy, well, gravitational force is one of them. That's what we're seeing here. You also have springs. Springs are a savings account for energy. If you stretch a spring, you're storing energy in it. You let it go, it releases that energy. You also have electric energy. We haven't seen that yet. And some other energies also have this same energy savings account type behavior. Well, how do we figure out what that savings is? Let's go back to this idea of our ball, right? We're going to have our ball at the bottom. And when we're at the bottom, it's going to have some speed v initial. And that speed is going to be upwards. We're saying this is maybe right after the bounce. I'm going to draw my soccer ball here again. It's going to bounce up and it's eventually going to reach its highest point. And as it reaches its highest point, we can say that this speed is zero. Everything, when it gets to its highest point, we call that the turning point, right? And that is when the speed becomes zero. And we analyze the energy. Well, that's easy. The energy at the bottom, we have a kinetic energy equal to 1/2 mv initial squared. At the top, we have a kinetic energy of, well, zero, because our speed at the top is zero. And then we ask the question about potential energy. Well, where did this 1/2 mv squared go to? That 1/2 mv squared must have gone into the potential energy. So I'll say that's 1/2 mv squared plus whatever potential energy we initially had down at the bottom, or we could say that our potential energy is some initial value. Whatever that initial value is, it's maintained there. Let's say we had 20 joules saved up for whatever reason. That 20 joules is added on to the increase in our kinetic energy. And then the question becomes, well, if this is our potential energy at the top, call that P final, potential energy final minus potential energy initial is equal to that 1/2 mv squared. And we can call this the change in potential energy. And what's interesting is whenever we're talking about potential energies, we're almost certainly concerned with some change in potential energy, not necessarily a potential energy at any given point, although we can make definitions to make absolute values out of specific points. And we'll see that later. So can we figure anything out, though, about this half mv squared? Well, certainly we can. Because what we know is the work done on an object is equal to the change in kinetic energy. That's the work kinetic energy theorem. If we view this system as being part of if we view the system in terms of work and kinetic energy, we could say the work done by gravity is equal to the change in kinetic energy. The change in kinetic energy, well, if we say initial is at the bottom, is going to be the final kinetic energy minus the initial kinetic energy, or negative 1/2 mv squared. And what do we know? Well, negative 1/2 mv squared, that's negative the change in potential energy. Right? Our potential energy is half mv squared, or our change in potential energy is 1/2 mv squared. So that means that our work done is the negative of the change in potential energy. The work done is negative change in potential energies. This is I derived it in this one certain case, but this is actually a true idea, that the potential energy, we often write it instead, that the change in potential energy is equal to the negative of the work done. So if we go back to our goals, right? First goal, how are these two things related? How are work and change in potential energy related? Well, the change in potential energy ends up being the negative of work. All right. And so we have this idea now that change in potential energy is negative of work. But what about this zeros thing that I was talking about? Well, if we go back to our soccer example, and I'm going to erase a bunch of this. If we go back to our soccer example, we can define our kinetic energies, right? Our kinetic energy at the bottom is 1/2 mv squared. Our potential energy at the bottom is some initial value. If we look up at the top, we have that our kinetic energy is equal to half mv squared, but our velocity is 0 here, so 0 joules for our kinetic energy. And our potential energy at the top is going to be equal to our 1/2 mv squared plus our initial potential energy. And what we can do at this point is make a decision about what we call our origin point. Our origin is a place where we call the value at that location 0, right? And we've discussed this in terms of position. We say that some object at the center of a coordinate system is 0 position, but we can do that with energy as well. We define where we want 0 potential energy, and here we might say our potential energy is 0 at the bottom of our path. And when we do that, our potential energy at the bottom is 0, meaning our potential energy final is equal to just 1/2 mv squared. Easy enough. Well, that is one choice, right? We could make other choices. We can say, for example, take away all of the blue that I just put in. We can say, for example, what if we chose instead for our top position to be potential energy equal to 0? That is a choice that we can make. And when we do that, what we are saying is that 1/2 mv squared plus potential energy initial is equal to 0. Or in other words, potential energy initial is equal to negative 1/2 mv squared. And that tells us what our initial potential energy is. And it is still true that our change in potential energy, our potential energy final minus our potential energy initial, it is true that our change in potential is still going to be equal to the work done by the work energy theorem. It's still going to be 1/2 mv squared when we take 0 and subtract off negative 1/2 mv squared. We still get the same value. So we get this idea now that What does it mean for something to have zero potential energy? Well, that is just where we choose the origin to be. And we have freedom to make that choice. And you'll see that there are cases where the choice is a little bit more obvious, a little bit easier to work out. There will be times when the choice is just totally arbitrary and it kind of doesn't matter. And then there will be choices that we will define zero to be a certain value because of convention. Okay, so this is just a brief rundown of potential energy. After this, I want you to watch the video on what we call conservative and non-conservative forces, and then that'll lead us into the idea of conservation of energy. All right. I hope this was clear. If you have any questions, please let me know. Otherwise, I'll see you guys next time.